My name is Peter Kriens. Been involved in OSGi, been involved in modularity since basically 1978, a long time. Now, there is this surprising coincidence. Brian and I talked this morning, and we found out that we basically used exactly the same theme, maybe a different angle, because I started about 4 billion years ago. I think Brian was a little bit longer out, but not that far. And to explain modularity, I also went to exactly the same, without synchronization, examples. The oxygen ion, when the universe was created, it was basically plasma. You had ions all over the place. And the first thing that happened in this modular world was actually the bonding of the hydrogen atoms, which created a completely new molecule that had very different qualities and behavior from these hydrogen and oxygen ions separately. And I think that's a crucial thing to understand, is that you can take three things that do not have a quality, but when you group them together, they get a new quality that is not visible in any of them, but it is only visible in the whole of them. That is a building block that nature, the great programmer in the sky, used extensively in a recursive fashion. And this presentation is largely about that recursion that takes place in nature, and that actually in our artificial simulation world of computer programming, I'm not sure I buy the simulation part, but I see that what we do is create simulations. We use exactly that same technology. And a couple of the problems we have in our world, I think when we look at nature, we'll find solutions to that. So bear with me, there might be some overlap, but my slides look very different from the beautiful pictures that Brian had. So nature did the same trick again. It bonded hydrogen and oxygen atoms, and there were a lot more ions. We had the carbon, which is basically the base of all organic molecules. We had the nitrogen, and they don't really know how. There's been experiments in the 50s that with lightning and putting a lot of the basic molecules into a primordial soup, you actually get these higher level complex atoms. Maybe it's the only explanation we've got. So we got these higher level structures that when you combine them further, and the big trick, the biggest invention of nature was really the phosphor atom combined with the oxygen and the hydrogen and the nitrogen, creating a molecule that was absolutely frigging amazing. If you think, it's mind-boggling. I'm not religious, but when you look at this and you look at the chances, and how little we know how that works, it's amazing. We got this nucleotide that has 3 different groups. Just by grouping these atoms, depending on the place where the atom is, it creates a different function. That's like what programming does as well. The phosphor group is actually creating a bond with the sugar group. And because of the shape, not because of the atoms, not even because of the bonds that they have, but because of their shape, they actually create an attraction to each other. This phosphor group can attach to another sugar group. So what you get is a nucleotide, and there are actually 5 of them. This is for the RNA, the A one. And the RNA molecule, which is much simpler than the DNA molecule, the double helix. The RNA was probably before. You can combine them together. These phosphor groups, sugar groups, they actually tie together, and you get a shape. Again, this is all about shapes. And this shape can match its opposite. So you can combine one of these other nucleotides, and if you do this, and because these phosphor sugar bonds tie together, you actually replicate an existing structure. In this case, the opposite, but you can do that twice. So likely life started by having these change of nucleotides, and they grew to long lengths. And because of these forces, these nucleotides can also attract in the same strand of RNA. They started to fold, and because they fold, they became little nano machines. That was probably, as far as we know, the source of life. The problem what we ran into, and I think every developer here in the room will recognize that feeling, the problem was complexity. If you had these RNA strings and you had the nucleotides floating around, then you got too much chance to get bad connections, to create bad strings. What nature needed was a way to create an encapsulation, to create a private space where you can do things on the inside that are not influenced by the outside. That is the key thing we do in modularity as well, and we'll come back to that in a little bit later. But what nature did, and it's a freaking miracle. It looked like the RNA molecule was encapsulated into a membrane, and it became a little home for the RNA string. And because it was now alone, the molecular engine, the plant that the RNA string was, could actually work on its own in that cell, not interfering with all the other RNA strings that were outside the cell membrane. So to create complicated things, you sometimes actually need a simpler environment where there is less chaos, where there's less possibility to do coupling to things you don't want to couple with. If you're a developer, you will recognize this, and you will recognize what happens in a big monolithic application. You need modules. So the cell is the archetypical. We had the grouping. You saw that by grouping things together, you got new functionality. The cell allows you to create a space, a safe space, as they call it nowadays, where you can actually be experimenting and doing your thing without having interference. Again, they don't really know why, but this freaking cell, basically all our cells, seem to originate from one primordial cell. And that cell got the capacity to divide itself, just like the RNA could already replicate itself. But the cell is basically the computer of nature. And by replicating itself, it could solve a lot of the problems. And then Brian already indicated this. There's this magic thing that happened. These cells started to replicate, they started to double, and they started to double. And they started to do the same trick again. Instead of just being a cell and one big soup of cells, they started to group together to create new kinds of functions. And that created our organisms. That created the heart, that created all these examples that Brian actually very nicely already showed. So what that allowed us to do a step in complexity, because this is all about complexity. How do we handle complexity? The cell was a fantastic building block to increase the complexity we could handle and not get the complexity. You know, when you work on a big application, the complexity is enormous. It's very hard to get things done. It's only when you can break it down to smaller problems that you can actually make progress. Sorry. Let's move forward a couple of billion years. And this was one of the first attempts at creating a computer. It's the Babbage Analytical Engine. What you see is probably the reason why it didn't work at the time. The design was not modular at all. Design tried to do everything at once without really breaking things in smaller modular parts. And at that time, the technology that they used to build the mechanical machine, they couldn't get the accuracy that this whole thing required. So that failed. The next time we did the attempt, they actually started with the smallest module that we know. They started with the bits. And this is a bit is a bit like the ion we had floating in space. We had a lot of them, But there were fortunately only 2 of them. What we did, because we couldn't handle that, we humans are very limited in mental capacity. We needed to have higher level abstractions to be able to understand what something is doing. This random bit of strings doesn't mean anything. So the first thing we did is actually group these bits together and let them form higher level molecules. And I wonder if anybody is old enough in this room to read these hexadecimal digits. Anybody can see which processor this is? No, you're all too young. It's an 8085. I can still read it, actually, after 40 years. But again, hexadecimal numbers are hard to remember. They don't mean anything to us. So we chunked them together. We put them, instead of using these easier to understand than bits, but still hard to understand for us humans, we gave them names. And we wrote wonderful programs with assembly code. There's been huge systems. I've been building large systems with assembly code. But everybody that goes there knows that there is a limit, that you reach the end of your spaghetti code relatively easy. We could not build systems with the functionality we have today if we had tried to all build them in assembly code. So we needed to move to some higher level. In the 60s, we got higher level languages. And I think that's the first time when we see the encapsulation taking place, when we got functions. When you have a function, you have an input, the parameters, you have an output, the return value, and you have an encapsulation, because what happens in a function is supposed to stay in a function. It's not supposed to escape. Your temporary variable in this example is not visible to the outside world. You might call it differently, you might turn it into a float. Nobody will know, as long as you obey the contract of that function. Return the int, which is the average of the array that you give. That's a crucial concept. It allows us to make modifications. It allows us to have our own little world inside that function that is not visible on the outside. When you make software, you don't make a one-time thing. You make a thing that's going to live for a very long time. I have programs that I wrote 40 years ago that are actually still running. You need to be able to evolve that software because new things happening. You need to be able to take advantage of new technology that comes around. If you have your private little space where you can do what you want, because there is a contract that other people depend on, they don't depend on what's on the inside, they depend on the contract. That's a crucial concept, and keep that in mind. But for the sake of this presentation, let's treat this function as a block, because it's not a black box, but it's purple here, but it's supposed to be red over there. The red box has a defined interface. We got the array going in there. We got the average coming out there. This in software, I think, was the first module. A lot of people don't see a function as a module, but I see it as a module, the first one. It's a little bit odd, but it is a module. What we do in nature and what we do in software is we group things together. We put them in a library. We actually rarely make a single function. We have a lot of these functions together, and we form them into what Niklas Wirth in the 70s, I think, or 80s, called a module. Now, a module has its own data. It's a set of functions. But actually, what we did in Java in 96, or in 93, whenever they got started, we named the typical Wirth module, we called it a class. Because there's some advantages. You can instantiate a class. It's not relevant for our model now. But in a class, we see this pattern appearing again. We have some stuff we export, make visible to the rest of the world. We have some stuff that is private to our class, the private and package private and protected maybe methods in that class. They're not visible to the outside. We can modify them without breaking anybody in the future. And that's a crucial part to understand with modularity, being able to change without breaking people on the outside. And of course, we import stuff from the outside world. So this pattern, export, public methods, private methods, and import is crucial for modularity. So we group it, and we have a new concept. We can now think about classes. When we discuss classes and we make a design, we don't worry about the internal methods. We worry about the class. It's another level that we can think about stuff. What they did in Java, actually, and Gosling called it the module, he introduced a package which is supposed to hold a number of classes, and we see the exact same pattern appearing. We have a set of public classes, we have a set of private classes, we import classes from other packages, and we export classes to other packages. It becomes a little bit boring, this repetition, but it's an important part to realize that we apply the same pattern over and over again. So when we got the package, in Java, we're putting those packages in a jar. And I think Gosling made a mistake there, because he didn't really follow the lessons of nature and software. He basically just grouped the packages, but he didn't have private packages and public packages, and he didn't have imports and exports. That's a crucial oversight, because that meant that on the level where things really got complicated, building systems, if you look at the open source world, there are hundreds of thousands of applications out there. If you put them in a jar, and I use it, then there's going to be clashes, and there's going to be compatibility problems, and I think Liferay has been there. That's the reason why they chose OSGi a couple of years ago. When you try to put everything together, you get the same problem as the RNA molecule had. Things start to interfere with each other, and you're just chasing bugs instead of developing new functionality. So OSGi in late 90s, early 2000s, decided to not call that jar a jar. They gave it just a new name. They called it a bundle. And a bundle was actually applying the same modular trick. Let's make some packages private. Let's make some packages public. Have the imports, have the exports. So this bundle is following that same rule. The jar, a bundle is a jar, but it puts some extra rules around to make it a proper module. I want to go a little bit more into that visibility, because there is a huge reduction of complexity if you properly understand. A lot of people know that modularity is good, but why? You have a part of your bundle that is exported. It's visible to the world, which means that if your bundle escapes in the wild and other people use it, they have a dependency on it, which means you have the obligation to not change that code in a way that will break their code. That is a huge, huge, huge constraint in how you can evolve your module. Yeah? So what you really want to do, you normally want to have as much private code in your bundle as possible. The more private, the more stuff in your bundle that nobody knows anything about, the easier it will be to create a new version where you can do wildly different things within the constraints that your export put on you, of course. And we have the imports. So those are the three key elements to realize when you talk about a bundle. So let's take a look how it used to look on the jar, on the class path in your VM, in your simulation. If you look, then everything was visible to everybody, even your private code, the gray parts, and your public code, the interfaces that you specified, they were all in one primordial soup of bytecode or class files, your class path. If you put these bundles around it, then something funny happens. Because you're a single person, your perspective is important. And when you have your perspective, you work from a bundle. You write your code in a bundle. So because of these bundles, because of the encapsulation and the protection that you get, the lower bundle on the left, I'm very bad in left and right, so the one where we see all the different parts yet, can only see a fraction of the class path. Because it can only see a fraction, it cannot couple to a lot of things that might be broken in the future. That protection is crucial. We all, as developers, intuitively feel how important that is. But there is a mathematical law as well that is really intriguing, that tells you why it's not just easier because it feels easier, or because our humans are having to look at fewer things. There's a mathematical thing that when you get a bundle and it is connected to another bundle, when you do that with two different things that get coupled, you add two connections. Let's now add a third part. We add 6 connections. Then we add 12 connections. We have 30. So when we grow the number of connections, we do not have a linear function. When you add a new node, there's actually an exponential number of connections possible. And when you look at software complexity is really proportional, or exponentially proportional, to the number of connections in your code. So it's very important to realize that two things that are very loosely coupled are less complex than the same complexity in one box, where things are more tightly coupled. So if we look at how that, that looks like, let's say that we got a piece of functionality. Let's represent that as a box. That's your program. And you make it a monolith. And when we look at the complexity, it would probably look something like this, because it's an exponential function. We get slow growth at the beginning, and in the end, we go up quicker. So what would happen if we look at that code and we break up that functionality into two pieces? If we now look at the complexity curve, it looks quite different. We're going to get two complexity curves that actually live a long time in the first part of the complexity curve. So you significantly reduce the complexity. By cutting the program in half and having two programs, we can seriously reduce the complexity, and the only reason is the mathematical formula that an exponential curve, if you cut it in half, that the sum is less than whether they are together. And that's related to the coupling that you do in your code. Now, that's easy said. What does it mean in practice? Let's say you got a whole bunch of classes, and those classes are heavily coupled. They depend on each other. We all know this. Every developer knows this. This thing, you wrote a beautiful application, you wrote 100 classes, and then you write your next application, and you think, that really fantastic class that I wrote, I actually want to drag it out, and I want to use it in my other system. So let's try to do that. Then we usually get this feeling that you got some chewing gum in your hair. You know, this was the reason I was very frustrated with objects in the 80s, because I thought we would get reusability of those classes. And because of this coupling, we didn't get it, because we didn't really take care of it. So let's go back to this picture. How should you do it? I admit this picture was prepared specifically for it, but there are some clear boundaries where you can actually cut these classes very nicely. You see, we have a lot of connections on the inside, but we have few connections to the outside. And now, in reality, when you have a monolithic application, and Liferay can testify that, and you try to extract these parts, it's almost impossible. It's very hard. It's a very expensive thing to do. It's a very hard thing to do, because people do not take care of it when they write software. We as a developer, we take a shortcut. We really want to go there, and we think that the shortest line between 2 points is a straight line. The shortest route between 2 points is a straight line. It often really isn't. Often you really have to have some indirection to make sure that you can get these nice, clean designs. But if you do it, you get reusability. So let's go back to modules. These modules then, if we extract them, we have basically changed the problem of internal coupling to external coupling. We get dependencies. We actually depend on another module now, and unfortunately, that other module is going to bring in a whole bunch of dependencies. Who is using Maven? Yeah, well, you all now, well, Maven doesn't download the internet. It's people that download the internet, but it doesn't feel like that. We have this big problem that this sea of dependencies is killing us. Let's take that it's not only killing us because it's complex, and that when you try to get a dependency, you got the feeling you keep on having to download more and more stuff. There's also a very logical problem there, that when you got the diamond problem, you got 4 bundles. And bundle A depends on B, it depends on C, and B and C both depend on D. You're screwed if they happen to depend on a different version. Because this is an unsolvable problem. And when you look at Maven users, how they have to wrestle with this case, that if it happens that the same library in different versions is in your class path, you have to exclude it, you have to do a lot of work to... oh, actually, I missed one slide. If you get this case, you're in problems, because it's very hard to solve, and certain cases not solvable at all. How do we solve it? Well, the key problem is that one bundle actually creates this whole static graph of other bundles that it depends on, or jars that it depends on in Maven. One bundle, and it's completely defined what the dependency graph is, transitively. But it is huge, and it's not what we want. Let's go back to nature. If we go back to nature, to the cell, how does he solve it? That cell does not have a POM pointing to another cell. Yeah, I can see it. And I'm reasonably on time. That cell is having a dependency on other cells to do its higher level functions, to do your heart, to do your kidneys, to do your liver. They're not islands, they're not standalone. So how does that cell actually express its dependency? How does it really collaborate with these other cells? Again, it does not say, I need cell A14. It wouldn't work that way. The complexity would be overwhelming. That's exactly the complexity that we are seeing in our software world. That because of this transitive dependency model, we get faced with a very big dependency graph. So this cell, actually the solution that nature found to this problem is what's called a receptor. The cell has a boundary, the membrane, and in the membrane there are what they call receptors that pierce that membrane. And they signal by molecules, and they signal by very specific molecules. If you translate this to software, they signal basically like a type. You can see this receptor is of a specific type. That's a beautiful model. So how does it work? Another cell can come in. Yeah, it's arriving. And it can eject a module. And that module, not module, molecule. Words are too close together. That molecule will go through there. It's not the exact same molecule, there is some signaling going on. But if you look on this from a logical level, what does the one cell say? It says, I got type X. Can anybody provide me with type X? Yeah? That's a very interesting concept. It's the concept of a broker. And it removes this problem that this one cell has to know about every dependent cell that it needs to collaborate with, which is really good for reuse because these molecules do not have to be emitted always by the same cell. There could be a JUnit test cell that actually emits the molecule just for testing the cell. That was a joke. So going back to the dependency model, how can we translate? How can we take that idea of having this receptor where the cell does not know about the universe, but can just express, I need this, or I can provide this. And that's what in the OSGi we call the service. It goes a little bit deeper, but in general, it's the most expressive part of the dependency model in OSGi. Instead of saying, I need module B 1.4, you just say, oh, I would really like to get somebody that has an event admin service for me. That's a very different thing because the event admin service or any other service could be provided by many others as well. So instead of signaling the implementation, and implementations usually have a very large transitive dependency graph, you signal, this is what I need. And in this case, I just need somebody to provide event admin. And you do not care who provides it. So going back to this really impossible to solve problem that you have when you specify a complete dependency graph, how would that look with a service model? With a service model, it would look like this. You would, instead of coupling module to module, you would couple module to service and service, and well, actually you would couple always from module to service. Some people would use the service, they would depend on the service. Some people would actually require the service. You can see here why this is such an incredibly cool model. Because in Maven, if I wanted to correct that problem, that we had these two different versions, we had B and C depending on the same thing, but in a different incarnation, we couldn't solve it. We would break our own system. We would have to change the transitive dependency graph. And in Maven, we have to make exclude and do all kinds of nasty things that in the end result in something that is not really proper. In an OSGi world, if you specify your interfaces, your coupling to other modules, just like nature does with the receptors, if you use this service model, then it allows you to make very significant changes in the structure of your application, in the structure of how your modules are put together in runtime, and you do not break everybody else. So instead of a very static, rigid, transitive dependency graph, you get a very fluid. Now, no beautiful thing like that works without cost. So what is the cost? Because we're still having this problem. The fact that we don't see the dependency graph anymore doesn't mean that it went away. We still have that problem of which bundles do we actually put in our runtime. So in the OSGi world, and we worked very hard in the last few years to really make that work. The module is actually already 15 years old. It started about 15 years ago. But we didn't really get it to work until maybe the last 2 years that all the tools are coming together. What we're doing is we're putting all those bundles in the repository. And we have a language which describes their requirements. What do they need? What services do they really need? And their capabilities. What actually are the services that they provide to the world? So the receptors and the molecules. But there's no human that can solve that constrained language because there's incompatibilities between bundles, there's missing, it's a huge NP-complete problem actually. Fortunately, there's a thing called a resolver. And I think it's one of the most exciting things in this model. Because now you want to have an application, and you have a sea of reusable bundles that are really capable of being used in many different contexts. So when we have this resolver, we can pick one bundle. We say that is our root bundle. That's the functionality I want. For example, this is my user interface for my game. That bundle will need services and other dependencies to make it function. What the resolver does is says, if you give me that bundle, I look at the requirements. And I'm going to find a bundle that has the capabilities that satisfy those requirements. And then I select that bundle, and that one will have more requirements, and I will find the other bundles that will satisfy those requirements. It's a recursive process. So that resolver is going to do a lot of hard thinking. Think. And when it found the solution, it will actually give you a number of bundles. Says if you put those bundles together, then you have closure. Then all the requirements are met by the capabilities of these other bundles. And when you run them, instead of what we normally do with Java, dump them on the class path and try things until you don't get a class not found exception anymore, and never really look what kind of unnecessary things are there. With this model, we only get the bundles that we really need. If you use B&D tools, you have a little command line application, it doesn't work, you drag in X-ray, a debug tool, and then the resolver will automatically add the web console, the web server, and all its dependencies. It's a fantastic model. I got one more minute. So we take these bundles, and that gives us an application. So the key difference between the Maven model is instead of that each module specifies its own hard, static, transitive dependency graph, which is very rigid, it's amazingly rigid. We specified requirements and capabilities, and we let the resolver create our application. That allows you to create many different applications out of a set of reusable bundles. And I got 2 more slides and 1 minute. Back to reality, back to the world as it is today. A picture from the moon, summarizing the conclusions. Modularity is nature's favorite trick. I think Brian showed that, and I think we fully agree on that. We might disagree on the simulation, but we definitely agree that if it's a simulation or something else, modularity is nature's favorite trick. Grouping provides new functionality that is not visible in its constituents, which allows you to reuse things in many different situations. And as humans, it's easier for us to understand when we can name it by a group instead of by an individual. It's individuals. Encapsulation reduces the interactions with the rest of the world, which create a protected, safe space, which allows us to grow things and evolve things over time without breaking people that actually depend on us. We don't get this ripple effect that is often so horrible in monoliths. Dependencies, and that's actually the only lesson. I think I've talked about a lot of things that everybody in this room is very well aware about. But there is one thing that I find with developers that they don't see. They see the Maven hard transitive dependency graph as a solution. I hope that you pick up with the dependencies. There is an alternative model that is closer to what nature does with cells, that works with requirements and capabilities. It's very new. Tooling still has work to do, but I think it's one of the most exciting things that we learned. And in the end, I've been working in this industry for 40 years, and there's always been one sacred goal in my life, and that is make software easier. And I always thought that reuse was the way to do it. I work with a lot of people in the industry, and I don't see that often enough, that people really work for reuse. People often take the shortcut and build things that are highly coupled. I hope that you picked up this from this presentation, and that when you write software, you try to get that reusability, small, uncoupled, highly cohesive components, because that's the goal. Thank you very much. 21 seconds.